Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is field challenges of measuring transformer winding resistance and on-load tap changer troubleshooting. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Samir Kulkarni, Applications Engineer. Also, to assist with the question and answer session, we will have joining us Daniel Carreño, Applications Engineer, and Ollie Benzler, Applications Engineer. All right, let's go ahead and get started. Thank you for joining us today, Samir.
Good morning, everyone. Thanks for joining us today, and thanks, Michael. So welcome to our Testing Tactics webinar, and today's topic is going to be field challenges of measuring transformer winding resistance and on-load tap changer troubleshooting. So let me start by going over the agenda. So first, we'll start with some fundamentals and measuring principles that are involved in transformer winding resistance measurement. Then we look at some basics of on-load tap changers and different types of tap changers that are in operation. Then we look at a few cases where we look at different aspects of a tap changer and how they interact while testing and how we can find or diagnose any issues. And then I want to leave you with an advanced diagnostic procedure, which is called dynamic resistance measurement, before we go to our summary and then take questions. So let me get started. So transformer winding resistance testing, it's a popular test that's performed during manufacturing, where you want to perform design verification, and it's also used for quality control. In addition to that, it's also used in the field as part of routine maintenance or during troubleshooting activities. So what is winding resistance measurement? So it's a low resistance measurement where you are trying to measure the resistance of the transformer winding. And typically, if you review test data, and inherently the value of that resistance is relatively low, and that would mean using the right methodologies to make an accurate resistance measurement. And the best way to do that is by using the 4-wire method, where you have independent sets of leads. One set will inject current into your test specimen, and then the other set will measure the voltage drop that is generated because of the passage of that current. So that's a quick visual on the right hand side of your screen. So where you have 2 sets of leads that will inject current into your winding, in this case H1, H2, and then you'll have a set of voltage leads that will measure the voltage drop resulting because of that. Now, at this point, I want you to concentrate on this equivalent circuit of the transformer. You can see that our main interest is the resistance of the winding, but that is not the only component that's in the circuit there. You also have this inductance of the transformer winding that's coming into play. And that becomes really important that you are aware of this fact and how you would want to address the fact that we are interested in the resistance measurement and not necessarily inductance. However, a transformer is an electromagnetic device. It works on the principles of electromagnetic induction. And that's why inductance is an inherent property to transformer operation. And this inductance does not allow a change in current that's flowing through the winding. So whether you are passing a current continuously through a winding, let's say 5, 10, or 10 amps, it won't readily allow you to change the magnitude of that current, because the inductor is a magnetic component that stores energy. And if you try to change that stored energy, whether it could be 0 at steady state, let's say this winding is not energized at all, or it might be in service, whatever be the case, the inductive behavior of the winding will react to any change in current. And how it does that is by generating a voltage across itself. And that's why you will have the transformer winding that will generate a voltage across it. And on the left hand side of your screen, you can see this equation, which is the total voltage drop when you are trying to measure the winding resistance. So you have your resistive component, which is pretty straightforward using Ohm's law, which is current times the resistance of the winding. But then you have these two terms. One is L di over dt and the other one is I dl over dt. So these two terms are transient terms which are present because of that inductive nature and because of that inductive behavior of the winding. And we want to make sure that they are not part of our measurement. And as we discussed, our main interest is to make sure that the resistive voltage drop is being calculated and is being measured actually. And that's why these transient terms have to be zero or have to go to zero. And both those terms, the di over dt, the first one is the rate of change of current, and the next one, that is dl over dt, is the rate of change in inductance. And there are two different aspects to discuss here. And what is the best way to make sure that the rate of change of current goes to zero? That is by ensuring that you're achieving proper current stabilization. And when you want to make sure that the change in inductance is zero, that is done by ensuring that the transformer core is saturated. So after having met the two conditions, you are now at a stage where you will have a stable and resistive voltage drop that's measured, and from there you can calculate the winding resistance. And having had this discussion now, it's important to know that whenever you are injecting current into the transformer winding, the magnetic energy in that winding is changing. And depending on how large or how small the winding is, and by that I mean what are the ratings of the winding, it may take shorter or longer for different types of windings to achieve the proper conditions for measuring resistances. And intuitively, you should start thinking that if a transformer winding that has a larger rating, that has a higher current carrying capability, it will naturally have a higher inductive behavior. That means it may take longer to achieve the steady state characteristics. So we looked at current stabilization being an aspect or a measurement principle of winding resistances. So what should be the proper method to achieve current stabilization? So we'll start with test current magnitude. If you review industry standards, the recommended range for using the right test current is to be within 0.1 to 15% of the rated current. And we'll review both ends of these specifications. So if you have too low of a current, less than 0.1% maybe, what you would have is an inconsistent reading. And this can happen in situations where you are testing the same transformer winding today, and then you come back to it in 6 months or in a couple of years, and the resistance readings seem to be very different. So one of the factors of having that situation could be the use of the proper current. So if the proper test current is not used, then you may get an inconsistent resistance reading, or it even might be inaccurate. Now, on the other side, when you are trying to establish the maximum level of current, you want to make sure that you're not exceeding 15% of what the rated current of the winding is. And that's because as you pass more current, you have I square R losses that leads to heating. And the moment heating comes into picture, the resistance of the winding is going to change. And once the resistance changes, now you're in a situation where you're trying to chase a moving target, and that's obviously not our intent, and that's a very futile effort. So always remember to keep your current ranges between 0.1 and 15%. Now the second aspect we discussed was achieving the proper core saturation, and that is done by using the proper amount of open circuit voltage, or the proper amount of voltage that is applied to the transformer core. And we saw that transient term, that was the change in inductance. Now, in order for that term to go to zero, what has to be done is that the core has to be saturated. And let me share this quick information with you that the transformer core is made of magnetic material, and that magnetic material has several of these small, it's divided into domains. And as you are saturating the transformer core, all the domains are aligning themselves to the direction of the magnetic field, and that's what eventually leads to core saturation. And how you achieve saturation is through voltage and time. So applying the right amount of voltage for the right amount of time is going to give you a saturated core. And on the right hand side of your screen, I've shared a graph of the hysteresis curve of a magnetic material that can be found in transformer applications. So as best practice, it is recommended that you should be in the maximum or saturation flux region such that you get a uniform and repeatable measurement. If you find yourself in a situation where you're in the near zero region of this hysteresis curve, you are going to get an inconsistent and inaccurate winding resistance measurement. So having discussed those principles, let's take a look at a quick example. So this was an auto transformer. It was an 800 MVA shell type auto transformer, a fairly large transformer. And it had three windings. The primary was 345 kV, the low voltage was 143 kV, and then the tertiary was a 23 kV. Now, I would like to share some observations. So this transformer, we measured the winding resistance on this unit, and the resistance values on the high voltage winding took almost 15 minutes to stabilize. So you can see that, in a transformer winding as large as this one, it took a fairly, good amount of time for the readings to go through its transient phase and then to stabilize. But as you can see on your screen on the left hand side, the Bravo and Charlie phase readings have been shared here. You can see that both are in the 45 milliohm range and they're fairly close to each other. So this is that discussion where sometimes, depending on the rating of the winding, it might take longer to stabilize. But once they do, and if the transformer is in good shape, more likely than not, you're going to get consistent readings. And considering that this transformer and the winding was rated at a higher value, the discharging of the current also took as long as 45 seconds. So from there, let me move on to discuss another measurement principle there, that is of temperature dependence. So we discussed in the beginning of the presentation that you should not exceed 15% of rated current, because then you're leading to heating and you're changing resistance. Now, a similar discussion can be had when you're talking about temperature. We obviously know that resistance readings are temperature dependent. And when you're in the field, it's very tough to achieve factory level temperature conditions, obviously. And whenever you are trying to compare results with historical data or even with factory test data, it's important to make sure you levelize the playing field. What I mean by that is to convert all readings to a reference temperature. And those temperatures to which you have to correct will depend on the temperature rise of the transformer. This information is generally available on the nameplate of the transformer. So you can use the applicable temperatures to which you would want to correct your winding resistance measurement. And on the right hand side of your screen, I have this equation here that allows you to calculate what is the resistance at a particular desired temperature based on this formula. And whatever resistance you've measured, let's say today in the field, you can correct it to the proper temperature as needed. From there, I want to have an important discussion that is on safety. So we looked at the process of measuring winding resistance. We looked at all the conditions and factors that are important to making sure that a good and accurate resistance measurement is made. But it becomes equally important to make sure that whatever energy was stored in the transformer winding in that process is discharged correctly. So that's what I'm going to discuss now. So whenever you are changing the amount of current in an inductance, it's going to react by generating a voltage drop, right? And it applies whether you are trying to inject current into the winding or even when you are trying to discharge the winding. So that could lead to any arcing if the leads that are connected to the transformer are disturbed and if they're removed at the wrong time. So it's very important to be aware of these conditions. And because of that transient behavior, the voltage magnitude that might be induced when you're disturbing the leads could be high enough to be lethal to personnel. And in addition to that, it could lead to damage of the transformer that's being tested as well as the test instrument. So it's extremely important to be aware of these safety practices and safety aspects of measuring winding resistance. So how would you want to achieve that? What's the best way to discharge the winding? So now with modern technology, most of the test instruments are capable of handling this energy that was stored in the winding in the first place. And generally, you will have some sort of a ground circuit to absorb that stored energy. Many times, limiting resistors are used in order to discharge that energy. And that's usually achieved with a two-step process where the current is reduced gradually. And then as this current is reduced, the energy that's available is dissipated to ground. And then a visual indication of safety should be provided to the operator such that now it's safe to disconnect the leads. From there, I would like to take you to the residual magnetism discussion. Now, we understood how winding resistance is measured, what are the principles, what are the safety aspects. But now, even when you have discharged the winding, the transformer core is still magnetized because you've used DC, and that's not the normal operating state of a transformer. And that could lead to effects on other testing or even during commissioning or rather startup of your transformer. So it could affect your excitation current readings or your SFRA readings as well. And you do not want to be in a situation where the transformer is trying to demand high inrush current because of a magnetized core, because during startup you may trip some of the protection systems associated with the transformer. Obviously, you do not want to have a nuisance trip during that situation. So the best way to combat residual magnetism is by following the practices of demagnetization. So that's the most reliable method. And based on field experience, it is recommended that you demagnetize on the high voltage side and on the middle phase. So part of the demagnetization process involves changing the magnitude and polarity of the test current. So you can see on the right hand side, on the right hand side of your screen, you can see that the polarity of test current is changed from negative to positive through several cycles. And that's the concept of effective demagnetization. Now, you may have the question that what was the test current used? So generally, you want to use the same amount of test current that you used in the first place to measure winding resistance. So let's say you wanted to make a measurement at 1 amps or 10 amps in our case. You want to use the same current when you're trying to demagnetize. So after having discharged the winding, after having done demagnetization, now it's time for results, right? That's the main output of the test. That's what you analyze. That's what you allows you to complete or close a test and move on. So when you have results, these results are compared and they should be between 2 and 5%, whether it's within phases or pairs of terminal, depending on the winding configuration. And one of the other things that is often done is comparing the results that you get today with historical results. Maybe that was a commissioning test that you have, or maybe a previous maintenance testing that was done on the transformer. You want to compare these compare your present readings with historical results. The main caveat there is to make sure that the right temperature correction is used. And of course, you know, comparing your present day test results with factory testing is always going to be helpful as long as you're at the correct temperature for comparison. And we have industry standards such as IEEE standard C57.12.90, which is the test code for transformers, and then of course the C57.152 standard, which is the field testing guide. And NETA also has specifications in their acceptance testing and maintenance testing specifications. So from there, let's take a quick look at on-load tap changers. Now, one thing I would like to mention here, and these are the basics of on-load tap changers or OLTCs, is the intent of using tap changers is to regulate the output voltage of the transformer such that the load requirements are met. And operation of tap changers involves changing the turns ratio of the transformer to achieve the proper voltage magnitudes without interrupting load current. Okay, so from there, let's take a look at some types of OLTCs. The first one is the resistive type OLTC. In this case, one or multiple resistors are used in order to transition from one tap to the next. And these type of OLTCs generally have a relatively fast operation time. So like I've shared on the screen, they could be in the range of 40 to 60 milliseconds in some cases. And because of the fact that this is a fast acting mechanism or fast acting system, there isn't any use of bridging positions. You'll find these resistive tap changers common on many high voltage windings. And now let's take a look at a quick sequence, a quick tap change sequence. So I have here, diagram A. So you're on, let's say you're on your first tap, and I would like to bring out a couple of things here. So you're on the first tap and you want to move on to tap number 2. So that function of selecting the tap which you're on or which you want to be on is done by the tap selector switch. So the tap selector switch will move from, let's say you want to move from tap 1 to tap 2 to tap 3, so on and so forth. And in addition to that, you have a diverter switch that will divert the load current as part of the tap changing sequence. So from there, let's move on to the next stage of your tap change. Let's say you've selected to go from tap 1 to tap 2. So now you'll have the diverter switch that will come into play, and that will have your resistive type, that will have your resistor there, to which will be part of your tap change sequence. So you can see that now the diverter switch has moved to this resistor, and from there the next stage would be having the resistor for the next tap also in the circuit. And from there the next stage would be, now the diverter switch has completely moved on from your previous tap, in this case tap number 1, and now it has the tap number 2 in the circuit with that resistor in there. And then the last stage will be when that'll be the final stage where you have completed your tap change, your resistors are out of the circuit, and you are completely settled on tap number 2 here, or the next tap, wherever you want to be. So moving on from the resistive type of tap changers, next we have the reactor type. So in the reactor type, some sort of an inductive or reactive components are used. So in this case, reactors are used for the tap transition, to have a smoother transition. And in this case, the bridging position will be utilized where you could be on 2 tap positions simultaneously in the bridging position. And because these 2 taps are at different voltages, you will have circulating current that is generated because of this situation. And the preventative auto transformer design there is used to maintain this low circulating current. Okay, and whenever they are switching, the switching involved in different types of tap changer designs, whether it's arcing in oil or sometimes arcing in vacuum, you might see vacuum interrupters that are used. And this reactor type design is very common in the United States, where you have many low voltage windings that have on-load tap changers with this reactive or reactor type on-load tap changer. So having looked at types, I want to discuss another concept of on-load tap changers, that is the make before break sensitivity. Now, what the make before break sensitivity is you want to make sure that when taps are changing from one to the next, you do not want to have any discontinuity in the circuit. We looked in the beginning at this OLTC section that dropping the load current is not an option, right? And that's why using this make before break sensitivity becomes important to ensure that your tap changer is operating correctly. And if there is any shortcoming in that operation, whether it's a poor tap transition because of many factors such as maybe an open circuit or high contact resistance, you want to pick those during your diagnostic testing. And generally, whenever you have a lower time setting for your tap transition and it goes through and it passes, that would mean that your tap changer is in good operation. And with Megger instruments, what's happening is whenever the change in current is 90% or below, that would denote that the test has failed. So whenever you're moving, let's say from tap 16 rays to 15 rays, and during this tap transition, if the current drops below 90% of your set value, so let's take this example. So your test current here is about 10 amps, and you are moving from 16 rays to 15 rays. And if the current drops below 9 amps, that is 90%, then that would signify a failed trap transition, and your make before break would generally show as failed. Now, it's important to understand here that depending on the design of your tap changer and depending on the age of your tap changer, the results that you see may vary. So for example, if you have a new tap changer, or maybe if you're testing a resistive type tap changer which has uh, a relatively fast response time, you might be able to test them at lower or more stringent make before break settings. But if you have a reactor type or a tap changer that still works fine but just has been in service for a longer time, you might want to adjust your make before break sensitivity settings in order to accommodate those tap changers. So remember that every tap changer will be unique, and based on how it has been used, what is its wear and tear status, it's going to behave accordingly. So it's important for you to know and adjust that. And part of the results, just a quick snippet I'm sharing here, is whenever you go through tabs, you can see that the sensitivity setting that was used and whether the uh, tab transition went through successfully or not. So you'll either have a pass or fail setup, or diagnosis there telling you whether that tab change went successfully. So after having looked at some of these basics and principles for OLTCs as well, let's move on to a few examples. So the first one I'm going to talk about is associated with an OLTC as well, which had something to do with tap changer contacts. So let's take a look at it. So here I have a transformer which was rated at 345 kV on the high voltage and 34.5 kV on the low voltage side. It was 166 MVA unit, and it had a high voltage tap changer with 33 positions, and it had a reversing switch associated with it. On the right hand side, you can see a quick picture of the nameplate. So let me zoom in real quick to show you a couple of things. First is you have your voltages that are ranged. You can see 345 kV is your nominal or your neutral position. Then you have your dial position. So you can see those 33 positions from 16 raise all the way to 16 lower. And then you have your tap selector contacts. So, and then you have your reversing switch. From there, let's take a look at what happened with this unit. So winding resistance testing was performed and phase B and C resistances were measured. Now you can observe on the left hand side of your screen that there was no resistance measurement on tap 6 raise and 10 lower. You can see that there is just no reading there available at all. And even the make before break sensitivity, or that make before break test, had not completed. So there is no indication of whether the test passed or test failed. So this was something that kind of got us in that troubleshooting mode to understand what was going on. So as part of the analysis, we just mapped the resistance readings versus the tap position. So you can clearly see that there is just no reading available at these. Now, after analyzing it further, we realized that the 6 raise and the 10 lower positions both corresponded to the tap selector contact 11. And let me take you to that slide real quick. So here on the right hand side, we have the nameplate, right? So if you zoom in on the tap selector contacts, you can see that for position 6 raise, you use the tap selector contact number 11. And the same contact number 11 is also used for the 10 lower positions. So now we kind of started understanding what might be going on here. And because of that, it was recommended that an internal inspection be performed, because we now had a quote unquote smoking gun there. And when the internal inspection was performed, contacts on the tap selector switch were found burnt. So this is the a good example of how you would want to troubleshoot and how you would want to understand what's going on, analyze and make those deliberate steps in order to catch a developing issue. From there, we will move on to the next example on OLTC troubleshooting. So this is a case where a rewound transformer was being commissioned. So this was with a utility customer, and they had a transformer that they sent in for a rewinding and remanufacture in 2014, and they were getting ready to put it back in service. So before that, they were naturally doing their commissioning test. So I've shared the picture of the nameplate here real quick. At the bottom, you can see that the high voltage side is rated at about 230 kV with a low voltage side of about 13 kV. The transformer rating is about 33.6 MVA. You can see the rated currents there. And from a tap changer standpoint, this transformer had a de-energized tap changer on the high voltage side and an on-load tap changer on the low voltage side. So let's see what happened next. So winding resistance measurements were of course performed, and the high voltage winding passed without issues, and the readings were within spec at less than 0.1%, which was great. But when the low voltage winding was tested, and this winding had the tap changer, most, in fact all readings were beyond 2%. And let me show you that real quick. On the right hand side, let me zoom in. You can see that from 16 lower all the way, and I couldn't share the full all 33 tabs here, but you can see all the readings are beyond that 2% criteria that's laid out by industry standards. And I've shared the graph of how that resistance trace or that response looked like. And during my conversation, it was a discussion where the readings were taken across all phases for each tap. And what I mean by that is, once you were, let's say, on tap 16 lower, you are measuring the resistance of each phase, and then changing your tap, and then going to the next tap, and then getting the resistance measurements for all phases. So that was the method that was used. Now, in response to that, one of the key things that was recommended was that testing should be performed across all taps, one phase at a time. So you want to stay on the same phase and cycle through all the taps. And that's done because you need to maintain the direction of flux, and maintaining that proper direction of flux is going to be extremely important, such that you get a repeatable winding resistance measurement and an accurate winding resistance measurement. So I have a quick example here. For an OLTC, let's say you have three phases. You start out with phase A, you're at the position 16 lower. Then you want to stay on phase A. You want to keep injecting current in phase A and cycle through the taps, let's say from 16 lower to 16 raise. Then you want to move over to your phase B. Then you want to move from 16 raise to 16 lower, and so on and so forth. So using this method will allow maintaining the direction of flux in the transformer core that will give you an accurate and repeatable measurement. Now we did that, and there were several readings that were still greater than 2%. So again, we were scratching our heads trying to figure out what's going on here and what's the best way to address the issue. So after having several discussions, we decided that we should pursue a phase-to-phase measurement. So initially, we were measuring phase to ground. We were measuring, let's say, X1 to X0, so on and so forth. But instead, we decided that let's run a phase-to-phase measurement test. And after retesting, of course, all the test results were within specification. All the test results were within 2%. And that's right here. Let me zoom in. So you can see right from the 16 lower tap all the way through across all taps and across windings, the winding percentage difference is less than 2%. And the graph is like so on the bottom of your screen. So what happens? We just changed the technique that we used to measure winding resistance. So what do we do now? Go home, resistance readings are within specification 2%. All right, let's pack up, let's get lunch, let's get dinner, let's go home. Obviously, that's not going to happen, because there is some sort of a problem that we are being told here during the test, and it's important to diagnose the issue. So we troubleshoot further, and then we realized obviously that during the phase-to-phase measurement, the any voltage drop or the path that connects you to the neutral bushing is not measured. And by following that, we were able to get winding resistance measurements that were within specification. And that made us think that there could be a possible issue with the connection that goes to the neutral point of the windings, or the connection from that neutral point to the neutral bushing of the winding. Now, in this situation, it becomes really valuable to have any internal drawings of the transformer, like that will tell you what connections the windings are made, or rather how those connections are made, how the windings are interconnected. In this case, we had a neutral, how the neutral point is connected to the neutral bushing. But having access is it will be really valuable for going into these situations where you have to troubleshoot. But unfortunately, in this case, we didn't have those internal drawings with us. So we did some more thinking, some more analysis, more troubleshooting, and we just compared some measurements. So we compared the per phase readings. So whenever you make a resistance measurement from, let's say, X1 to X0, and we compared those sets of readings with the phase to phase, so X1, X3, for example, and we realized that whenever we had the X3 bushing in the picture, in the measurement, we were getting slightly higher results. And because we were at a point where we couldn't pinpoint, or we couldn't obviously understand what was the issue going on, like we hadn't found where the failure was per se, we said let's test further. So it was recommended that we perform another test, which is the SFRA test, to detect if there is anything that's going on, or that could be a issue that would be developing now and it could get worse over time. So after running the SFRA test, we we documented what the magnitude response was, and we saw that in the higher frequency region, that means in the 350 kilohertz or higher, the magnitude response was not coinciding, and it showed some differences. So I have a picture of that real quick. On the right hand side of your screen, you can see that all the three phases are very well coinciding, but in that higher frequency range, you can see that there is some mismatch in that magnitude response. And that high frequency area is generally represented by leads and connections. So now we were in a situation where we had our winding resistance test and the SFRA measurements both pointing us to some sort of an issue that was going on within the windings. And rather, we were able to find where that could be within the winding. So that could be within your connections going either to the tap changer or the bushings, something that would be represented in the high frequency region. So considering all of this, we said let's try and perform an internal inspection. So the customer did attempt an internal inspection, but because the unit could not be fully drained, it was very tough to find a smoking gun, so as to speak. But just sharing some pictures here of how whatever information that we were able to get. Now, of course, it's an important point to discuss here that although this internal inspection was not very conclusive, we still try to look at the measurements. We try to analyze the winding resistance measurement. We even perform some comparative testing using other testing techniques to determine or to corroborate if there was an issue going on. So in conclusion, we had a rebound transformer whose winding resistance readings were within 2 to 5%, and the winding resistance mismatch and SFRA test indicated some potential minor connection issues. And we realized that when we measured the phase-to-phase measurements, we got much tighter and much results that were even within the 2% criteria. So citing the criticality of this transformer and using information that's in IEEE standards literature, it was decided that the unit will be, they will go ahead and energize the unit. So I would like to share this excerpt from IEEE standard C57.152. It says here that comparison may also be made with original data measured in the factory, and the resistances between phases should be within 2% of each other. Agreement to within 5% for any of the above comparisons is usually considered satisfactory. So what they're saying is you want to make sure that you are between 2 and 5% of of your readings, and even when you compare it to your factory or historical results, you can use this 2 to 5% comparison technique in order to determine whether your test is successful or not. And like we saw, it is not always easy to find a fault, without extensive delay in repair time or outage time. So it's important to use the standards that are available to us, but also do our due diligence by testing, by analyzing, and even relying on comparable testing with other tests when you are in a situation with questionable results. And after that, we don't just stop, because we need to make sure that if there is any developing issue that is going on, we need to catch that. And the customer is going to perform online DGA, and it's going to understand the signatures of its dissolved gases, and they're going to train them over time to detect any issue that might be worsening. So with that, I would like to leave you with our last topic of discussion today, which is advanced diagnosis that involves dynamic resistance measurements, or DRM. So what is DRM and why do we want to do it? So we know that direct current is used to measure, static winding resistances. And in the dynamic resistance measurement, what is done is that this DC is maintained as taps are changed through the winding. So this graphing on the bottom left of your screen, it says that your winding resistance measurement is made. Let's say you're on tap 1, you get a resistance value. And while that DC current that is injected, it's the current is maintained through the winding, and then your taps are changed from, let's say, tap position 1 in this case to tap position 2, and this tap transition is reviewed, and this tap transition is documented. Then you move on to the next tap, and so forth. So the current and voltage signatures are plotted during this tap change at a higher frequency rate, or high sampling rate. They're sampled, and the results that you obtain, they are compared with prior benchmarks or prior baseline testing that you may have, and with sometimes with similar designs if you don't have a benchmark, just to understand how that response is. And then the type of problems that you may see that are diagnosed with this issue would be issues where slow transition time. So let's say you have a resistive type tap changer that has an issue with some internal springs, or maybe a resistor is having issues. You will see that during this test. Any discontinuity issues or contact problems, and even open circuits will be detected using the dynamic resistance method. So let's do a quick overview. We looked at how a tap is changed in a resistive type tap changer in the beginning, in the middle of the presentation. So now let's understand what happens from the dynamic measurement standpoint. So here I'm sharing the dynamic current measurement that was made on a resistive type tap changer. So now you're on tap position 1 here. You are in, if you will, you're in steady state. You're conducting load current, no issues. Now you want to change from tap 1 to tap 2, right? So this is your position A. So you're maintaining your level of current. Now you move to your next position, that is that you have that resistor in place. So the moment that resistor comes into play, your current is going to drop in response to that. As the tap moves along, where it has both the resistors in the circuit, you have the total resistance is going to be combined. It's a parallel resistance, so your current will still drop, but at a lower rate. Then as you move completely over in stage D, as you move on from tap 1 to tap 2 here, you can see that the current drops further. And after that, in your final stage, you have completely switched over to the next tap, and then your current builds back up to your steady state condition. So these are the stages that are monitored during the dynamic measurements, and in this case, dynamic current measurements. And there are two key parameters here that are the output of the test, if you will. First is the ripple, and then the second one is the slope. We'll look at those in detail as we move on. So we looked at dynamic current measurement in the previous slide to understand and explain the process. So there are three methods when you're dealing with dynamic measurements. First is the dynamic current that we saw. Next is the dynamic voltage, and the third one is the dynamic resistance. Now, the dynamic current and dynamic resistance methods are more common, and depending on what type of tap changer you're testing, you will get a response accordingly. So let's think that, for example, you have a reactor type OLTC. So for a reactor type, the dynamic current trace here on the left hand side of your screen will be used for analysis. But if you have a resistor type, you'll have the dynamic resistance trace that also will be available for analysis, because in the reactor type you don't have any resistances, whereas in dynamic resistances, you, like we saw here, you have Ra and Rb in this example of ours. So you will be able to determine what is the resistance of those transition resistors. So the parameters or the output of DRM testing is the ripple. So the ripple is the drop in current during the tap change. As you can see on the right hand side of your screen, your current level, whatever was the current level, will drop to some extent as you go through the tap change process. And the amount by which the current drops is defined as the ripple and is expressed as a percentage. Now, from an analysis standpoint, you want to make sure that the ripple is consistent across all taps in a phase. And if you see any sort of change or any sort of abnormal change in the ripple, that's something worth reviewing as to what might be going on. Then the second aspect or second parameter is the slope. So the slope is the rate at which the current will drop. And like we discussed in the previous slide, we have a transition time that is available as you move from one tap to the other. So for resistive type OLTCs, you will have the individual time that each resistor is in the circuit. And then for reactor type OLTCs, you will have the total time it took for the tap changer to go from one tap to the other. Now, there are a couple of excellent references to increase your knowledge on dynamic resistance measurement. On the left, it's a webinar that was conducted by our application engineer, Mr. Benzler, who's also our panelist for today. And the other one is a case study that was recently released where dynamic resistance measurements were made on a resistive type OLTC. It is an excellent read. I would recommend you guys to check out both of these sources in order to enhance your understanding on dynamic resistance measurements. So with that, let me move over to summary. So what should be your key takeaway from our discussion today? Remember that you are using current stabilization and core saturation to get that accurate and repeatable winding resistance measurement. So for that, you need to make sure you're using the amount of test current and the open circuit voltage in the best possible way in order to get good quality measurements. And remember that whenever you are comparing historical results or factory data, using temperature correction is very important to make a fruitful comparison. And if you find yourself in a situation where your results are questionable or they're out of specification, always remember to review what industry standards recommend and perform any complementary testing to corroborate or deny the issue. And advanced analysis tools are available, such as dynamic resistance measurement, if you want to further understand and go deeper into the operation of tap changers. Remember that it's a combination of test setup and the proper safety practices for you to have successful winding resistance testing. And then remember that my last slide here, remember that winding resistance is a diagnostic tool. It's used for design verification if you're on the manufacturing side, or it's used for field testing and troubleshooting. And the measurement of winding resistance depends on the design of the transformer, the construction of the transformer, as well as the capability of the test instrument that you're using. And then we looked at a few case studies where we looked at different winding configurations and different measurement techniques that gave us more information on what was going on with our OLTCs, and we helped to diagnose or at least generate a path forward for success. And then, of course, Megger is always available, and we are here to help you in any way. And we have our MTO series winding resistance testers, the MTO 210, 250, and the MTO 300 series available, as well as the MWA series, which can run turns ratio and winding resistance tests within one equipment. And of course, we have the tracks, which is a multifunction test set, which can perform tests for power transformers, circuit breakers, and substation assets as well. And one cool thing about the tracks is that it has the ability to run dynamic resistance measurements on your tap changers. So with that, I would like to end my presentation and give control over to Mike. Thank you.
So at this time, the presentation portion of our webinar has officially concluded. We'll now take some time to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On the survey, there is a field where you can also request a quote or a demo of any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for upcoming webinars on our website at us.megger.com/webinars. Our next webinar will be on June 30th, where we will cover best practices for mineral oil breakdown voltage tests. All right, well, let's jump into your questions. Our first question I'm going to direct over to Daniel Carreño. Daniel, which reference temperature should be used for a transformer with dual temperature rise of 55 degrees Celsius and 65 degrees Celsius?
Thank you, Michael, and hello to all of the attendees. Appreciate you guys. And I don't know if Samir can go back to that slide, right? I think he did cover that during the presentation. We want to convert the results or results of our measurements back to reference temperatures, because remember, the analysis of winding resistance values is purely comparative. You look at your either the factory results or previous measurements you have performed on that unit. Right, so typically, it's very typical that reference temperature is taken from that temperature rise value from the nameplate. So in the case that you have a dual temperature rise transformer, look at your previous results. You just check which one was used. Maybe they used both. Maybe they gave you both values, right? Converted back to both 55 and 65 degrees rise. And again, remember, you compare today's rise to the previous results, on top of course, the difference between phases. So just check your previous results or factory results and use the same reference temperature.
Great, thanks, Daniel. Our next question is going to go over to Ole Bensler. Ole, is the OLTC always in the secondary winding?
So hello, I don't know if my webcam started or not. Yeah. So this is a good question. And normally you want to place the OLTC where you have the neutral connection. So in the examples presented here, we had a DY-N transformer, and then the taps was on the secondary side. And these are quite common in the US, but here in Europe, it's much more common with YND. So then the OLTC will be on the primary side. The reason is because you will have it at 0 potential or at neutral potential, so it's an easier construction. But for larger power transformer, you sometimes have 3 OLTCs, 1 for each phase, and then it might not be as critical to have it close to the neutral. So it will vary where you are, but mainly where you have the neutral point. Yes, thank you.
Thank you, Ole. Our next question is going back over to Samir. Samir, how is the percent difference calculated for each position?
Okay, so yeah, that's a great question. So as far as calculating that percentage difference, what you are trying to do is you are going to first generate the average of all your readings. And let me quickly take you back to that slide with some results that will make it easier to understand. Just give me 1 second. So let's take this example. So when you want to calculate, you want to get first an average of all these measurements. So that'll be your R average. And then you want to make sure that you get the difference of your maximum reading with your minimum reading. So in this case, we'll take the average of these three measurements, and the maximum in our case is 21.20. So that'll be your R max, and then your minimum will be R min, that is 21.1. So you get the difference between these two. So that's your delta R. You divide that by the average, and then you multiply that by 100 to get your percentage value here. So that's the popular IEEE method that's used in the US to calculate the winding resistance percentage difference. Thank you.
Amir?
I
Back
can,
over to Ole. Oh, yes,
sorry,
of course.
Michael, just wanted to add a couple, or there are a couple of different standards, like Samir mentioned. Yes, I mean, here in this side of the world, right, the IEEE or ANSI, and as a matter of fact, IEC is the same. The formula that you use to calculate that percentage difference is the same, which is your maximum value minus the minimum value divided by the average. Then, of course, you multiply by 100 to get your percentage. But there's another standard, the CEE standard, that is a little bit different. You have to first calculate your maximum phase error, which is each individual phase value minus the average. Then you divide that by the average number again to calculate your percentage difference. And again, the two formulas are indicated in the standards. That's what I wanted to add, Michael.
Right.
Sorry.
Excellent. No, thank you. So next question is back over to Ole. Do nonlinear resistors have an impact on measurement?
Okay, like a non-linear resistor, then I think about a diode or something. But in some sense, all the resistors are non-linear because they're temperature dependent. But if we look in a power transformer, I can imagine that you can have some type of non-linear contact problem if you have some type of burnt contact. So for example, if you perform the dynamic resistance test, they usually say that you shouldn't perform it with too low of a test current because you can get false reading, because you have a very thin layer of some coating that doesn't get burned through, and then you can get false interruptions. So that would be one example of a non-linear, so to say, resistor. But when you perform the winding resistance measurement, I don't think it's very common that you have these type of problems. So no, I don't think that will affect the measurement in any real way. But for the dynamic resistance test, it can be a bit more sensitive if you have a quite good connection only for low currents. Yeah.
Thank you. Moving on to our next question. Daniel, on position C, resistor A and resistor B are in parallel. Total resistance should decrease. Why does current decrease?
Thank you, Michael. So maybe could you go back to that slide? I think it's 48 or 47. You showed right, that one. Great question, and I mean, very good eye, right? And if you look at position A, right, that's let's call position number 1 on the tap changer. So when the OLTC gets the signal to go to the next one, right, it has to go through all these steps to reach position number 2 or the next one, whatever the label is. So all these intermediate steps, right, B, C, D, are again just the transition. And of course, in the case of this specific type of tap changer, you need these resistors A and B as your transition paths to go to your next position. Remember, right, the OLTC is designed to go from one position to the next without interrupting the flow of current. So these two are transition resistors, and you can see from these diagrams that you are actually adding resistance if you compare this position to position A, which is an actual position, like position 1, right? We said that as an example. So you are adding resistance to that path of current in that transition. So that's why your current goes down a little bit in that transition.
Is it okay if I jump in, or was you done, Daniel?
Sure, go ahead, Oli, please.
If I understand the question correctly, he questions why the current drops when they are in parallel, because when in position C, RA and RB are in parallel, meaning we have a lower resistance, and this is also true. So if you see on the current curve below, the slope will in the middle decrease a bit, the slope. Yeah, in that middle part. And that's because we have a lower resistance, so we will have a longer time constant. So you are correct that when they're in parallel, the drop in current will decrease a bit, and that's because the time constant for the inductor, where we have this tau L divided by R. So when they're in parallel, we have lower resistance and the drop will be slower, but it will still continue to drop, and that's what's seen in the graph. Yeah, I think that answered it.
Well, while we have you, Ollie, I'll keep you on for this next question. Are there any special considerations in regards to the instrument needed to perform dynamic measurements?
So first, people were performing binding resistance measurement, and you just normally want to test all the taps for the same phase, because then you don't have to discharge, you can just keep the current stable. So what you then do is that you have in this state A, you have a stable current, and then you go to position E, and then you do your next binding resistance measurement. So at its core, the dynamic resistance measurement is that you only record the current when you go from phase A to E, so to say, or position A to E. So you only record your current when you also make the transition. So in theory, if your instrument can perform winding resistance measurement, it could also perform dynamic resistance measurement. You just need to measure the signal with a high enough sampling rate. So there's some numbers going around, but usually 10 kilohertz is so to say, we and some of the competitors use that as a minimum to be able to get a high resolution of the current when it goes from this stage. But then, for example, in tracks, we perform this dynamic resistance measurement where we get the resistance graph, and then we apply a voltmeter on the secondary side. So you will need to be able to handle these induced voltages that might occur. But in general, there's no big difference between an instrument that can perform winding resistance and the instrument that can perform DRM as well. You only look at the current. Yeah.
All right. Thank you, Ollie. Next up is for Daniel. Daniel, when testing outside in substations, if we start testing at 52 degrees Fahrenheit and end at 75 degrees ambient, do you ever see outside ambient have much more effect? I know normally we use the gauges for temperature on the transformer.
Thanks, Michael. Great question, and certainly a common questions that we get asked on winding resistance, right? Of course, you guys know, and we always emphasize that temperature is very important, right? It directly impacts the results. It changes the results, and as you correctly mentioned, right, the temperature you were after, the one you take, so you can correct the values, right? Samir touched on that on the presentation, and there was a previous question on the topic. So the one really important measure or temperature you look at is the winding temperature, right? Most transformers will have that gauge, that indicator of winding temperature. So that's the one you take to at the end of your measurements, calculate or convert back to your reference temperature. Yes, thank you, Samir. So on that case, right, when you start, let's say, very early in the morning, and of course the ambient temperature starts to increase, remember that, of course, especially for larger transformers, right, the time it takes for the internal part, in this case the windings, to reach equilibrium with the ambient temperature is too long compared to the time that you take to actually run your measurements. So now, of course, right, you can tell me maybe we come in the morning, we do the low side, and for whatever reason, we don't get to do the high side until late afternoon when the temperature already changed. Of course, then your high side measurements, you look at your gauge again, your winding gauge again, and take that reading and use that for your calculation to convert back to your reference temperature.
Thank you, Daniel. Over to Ollie. What about step voltage regulators? Can they be tested with DRM?
So step voltage regulators is something that you have in the US and we don't have here in Europe. But from my understanding, it's auto transformer, and you have connected a reactor, a preventive auto tap switch to part of that auto winding. So yes, they should be able to be tested with the same methodology that you test the reactor OLTC on your power transformer. Yeah.
All right, excellent. Next question's over to Daniel. Why does one phase have to be measured at a time?
Okay, that's a great question. I'll try to be brief. There are many factors. I mean, and I mean, starting with the short answer is not necessarily is not a requirement. That there are solutions in the market to perform three-phase measurements. But in the case of course a three-phase transformer, we have to look at the method that is used to actually measure, to accurately measure winding resistance. Right, as Amir explained it very well in the beginning. Right, we use the four-wire method. Remember, right? We are only after the resistive value of that impedance that we measure when we perform the test, right? That's why we need to weigh. That's why we need the voltage, the current. We're only after the resistive part, and that's also the reason we use the four-wire method, where we measure the voltage drop at the bushings, right, closest to the winding, or to the winding that we are measuring. Again, it is possible to do multi-phase, and actually most of our instruments can do two windings at a time, or even three if you have enough channels to measure. But when you talk about a three-phase instrument to measure, then if you look, maybe this is not not the best. I don't know if we have a delta or a Y diagram that we can show. But when if we don't have it, if you picture those two, right? If you have a three-phase source injecting currents, then you have to deal with summation of currents and then taking the right value of the current, and also take into account where you are measuring the voltage drop to accurately calculate the resistance. So what I'm point is, it is possible to do three-phase injection. The method is proven to not be more complex and sometimes not accurate of individual phases values. So yeah, again, certainly possible, but sometimes problematic.
Thank you, Daniel. Over to Samir. Why does the flux to obtain saturation not recorded and not used to on maintenance analysis?
Okay, thank you for that question. So the answer to that question is that the flux is used, but for the purposes of winding resistance measurement, you are more interested in making sure that you're saturating the core than understanding the saturation characteristics of the core with DC, because the transformer is, after all, an AC machine. So the flux that is used during the normal operation of the transformer, that flux is analyzed using the excitation current test. That's a test that's done by using AC quantities, where you will apply, generally, the industry standard is about 10 kV. So you apply 10 kV to the winding, and then you record the current that is demanded by the winding as part of that process. And that current that the winding demands is used to establish that baseline working flux in the transformer core. And excitation current measurements reflect that activity, and they are used and trended over time to determine any possible issues with your transformer winding. One note about excitation current is that it's typically performed on the high voltage winding of the transformer by keeping the low voltage winding open circuit. So now you're only concentrating on the amount of energy required to establish that working flux in your transformer. So it's done, but it's done using AC quantities, which is known as the excitation current test. Thanks.
Thank you, Samir. While I have you, can I also ask this next question over to you? In the case of a deviation greater than 2%, measurement of the winding resistance, giving the rest of the test well, and the results of a physiochemical and oil gases well, to which can we attribute this difference?
That's a great question. And I'm sure there are many of you that might find yourself in that situation where your winding resistance, maybe they are slightly beyond 2%, but your oil analysis, before the test or right when you're getting ready to reprocess the oil, all of those results look okay, they are expected. And it's not that the transformer was under a fault or anything, but you're still getting that slight mismatch. So that's why I made it a point to discuss that IEEE note and the fact that there is information in the standards that will allow you to accommodate these situations. And that's why it becomes important to have a reference measurement, let's say from the factory or from the last time the transformer was tested. And that allows you to understand the specifics of how winding resistance has changed, whether there has been a large deviation. And if it hasn't been, sometimes it could be the inherent behavior or the resistance is as is. Like in our case, that rebound transformer might have a slight mismatch. Now, that could be the normal state of that transformer. That may not necessarily mean that the transformer is degraded or has issues with its winding, but having that data point and comparing with historical data will become important there. So that's why you want to have some historical information or factory information that you can compare to. Thank you.
Thank you, Samir. It looks like we have time for one last question. I'm going to send that over to Ollie. How does high magnetization influence winding resistance measurements?
I don't know, great question, but Samir, can you show this saturation curve, so to say? Maybe we can look at that. I know you had one in quite early in the presentation.
Yes, let me take a look at it real quick. Is it this one that you're talking about?
No, take, well, I think one up a few more, I think, but you had like one where you showed the behavior of the core.
Okay, there you go.
Yeah, this one. So in this picture, this is a bit, so to say, enhanced. Normally it's very, very thin. It doesn't have all this large area in the middle. But when we apply this voltage, we have the equation to the left. We have voltage times time equal to the flux. So when we apply a voltage, we start to build up the flux in the core, and we will apply this voltage until a certain current is reached. Maybe Daniel can mute himself, because I think there's some. Perfect. And depending on if you apply, for example, 10 amperes, 1 ampere, or 100 ampere, you can see that the x-axis is current. So the higher current we select, the further up in the magnetization we will come. So it's a very, very small difference, but we'll still get further up, so to say. We will introduce more flux into the core to get this current. And of course, if we saturate the core even more, we will get a lower inductance. So the difference, or how it affects how magnetized the core is then how much inductance we have left, and that might affect the time constant to get a stable reading. So for example, 100 ampere will be will magnetize the core more, and then you will have a lower inductance, resulting in a faster stabilization time. I think that
just to add to that real quick is that with the process of core saturation, what having the core magnetized to the appropriate extent, what you will see on your test instrument would be a reading that doesn't change very often, or it doesn't vary with time a lot. So that's where you can understand that all your conditions have been met, where your current is stable and your core is saturated. So from the influence of high magnetization, what that means is you have a more stable measurement, and because of the fact that you're achieving that higher magnetization and you're achieving that core saturation, if you follow that technique all the time, it is more likely that you'll get a more consistent resistance measurement. That's all.
Yeah, and of course you have to go below the saturation point, else your current is not gonna. So you have to saturate it up until that point, and then depending how much more you saturate it will influence the inductance. There's also another aspect, but depending if you have 3 or 5-legged transformer, because sometimes if you have a 3-legged transformer core, it doesn't really matter if the other legs are magnetized or not, because once you magnetize one, the other will appear magnetized. But for a 5-leg core, that's really not the case. So then, if you have a higher test current, you can still have a higher voltage, so you can magnetize the other phases a bit faster. So that will also decrease the time, if I think about that correct. So yeah, thank you very much.
Excellent. Thanks, guys. It looks like that's all the time we have for our Q&A session today. We apologize if we didn't get your question live here, but we'll be working to follow up with you offline. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. I'll also try and attach those other assets that Samir had mentioned there at the end of his presentation. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all for attending, and I hope you all have a great weekend.